Okay, here's the first question. The pH of a 0.55 molar aqueous solution hyperbromeous acid HBrO at 25 degrees Celsius is 4.48. What is the value of Ka for this acid? So what you have to do is to start with like an ice chart. What you start with is 0.55 molar of the acid, but you don't have anything for your products. So you put negative x plus x plus x, and then 0.55 minus x, and you can ignore this x because the value is going to be so tiny. Since you have the pH, you can do 10 to the negative pH to get the concentration of H3O, and then you can just plug it in there. And since x plus 0 is 3.31 times 10 to the negative 5, that means that x is that number. So that is also the concentration of the conjugate base. So then what you have to do is asking for the Ka, so you do products over reactants to get 1.99 times 10 to the negative 9. So question 2 says the Ka of an acid is 3 times 10 to the negative 8. What is the pH at 25 degrees Celsius of an aqueous solution that is 0.02 molar in HClO? So what you have to do is to make an ice chart again, starting with the acid and then adding water, and you get the conjugate base and the H3O. And then you start with 0.02 molar of the acid, but you don't have anything in the products. So then you do minus x plus x and plus x. And then you can ignore that x because it's going to be a small number. Then you do products over the reactants. And then you have the Ka, so you can just put it in for Ka and then solve for x. X is equal to this number, and then you want the pH, so negative log of concentration of H3O gives you the pH. Question 3 says, using a data in the table, which of these conjugate bases below is the strongest base? So there's a couple of rules that you can use. It's like higher Ka means lower Kb, and then higher Kb means a stronger base. So in this case, the lowest Ka is for HClO, which is 3 times 10 to the negative 8, which means that it has a higher Kb, so it is the stronger base. So question number 4 says, on the basis of the information above, what is the approximate percent ionization of HNO2 in a 1 molar HNO2 aqueous solution? So what you have to do is to make an ice chart again. You start with 1 molar of HNO2, but you don't have anything in the products. You do minus x plus x and then plus x. And then you can ignore this x because it's going to be a small number. And then, so you do products over reactants. Since reactants is just 1, it's just going to be x squared. And then you have the Ka, so you can just plug it in. You get x to be 2 times 10 to the negative 2. And then to find the percent ionization, you have to put the number that you get after the reaction over what you started with. So 2 times 10 to the negative 2 will give you 0.02, and then it's asking for percent, so you multiply by 100, and you get 2%. So for question number 5, it gives us the Kw of water to be 1.14 times 10 to the negative 15, and then it's asking for the pH. So water is only neutral when it's at 25 degrees Celsius, so what we have to do is to just write the formula for Kw. It's like H3O times OH, and these concentrations are the same. So all you have to do is to square root the number of Kw that'll give you, and that's going to be the concentration of H3O and OH. And then it's asking for the pH, so you just do negative log of the number you get as the concentration. Okay, question number 6 says the pH of a 0.1 molar base is 11.86. The reason you know it's a base is because the pH is greater than 7, and it's then asking for the pKb of this base. So what you have to do is to make an ice chart, and then you start with 0.1 molar of the base, and then you have 0 and 0 as your products because you don't have anything at first. And then to find any other value in this chart, you have to do 14 minus 11.86 to get the pOH of the solution. And then you do 10 to the negative 2.14 to get the concentration of OH in the solution. And then what I did, I kept the number in my calculator because if you round it, you won't get the right answer. But I just put it here so you can see it. And then you plug in those numbers here, and then you can ignore this one because it was a tiny number. Then you do, to find the KB, you do products over reactants, and then you get the KB. After that, you can just do negative log of your KB value to get the pKb. So question number 7 says, which of the following substances will dissolve in water to produce an acidic solution? So I'm going to start with the wrong ones. Na2O, NaOH is a strong base, so it'll have a weak conjugate acid. So that won't do anything in water to create an acidic solution. NH3 is a weak base, so that's not even acidic. And then NaC2H3O2, again, NaOH comes from, it's a strong base, so the conjugate acid will be a weak conjugate acid. So the only right one is FeCl3 because FeOH is a weak base, so the conjugate acid will be a strong conjugate acid, so it'll create an acidic solution. Question number 8 says, what is the pH of a 0.11 molar BaOH aqueous solution? So what you have to do is to start with the equation, and then you start with 0.11 molar of the base, and then you don't have anything as products because you just started with nothing. And then since BaOH is a strong base, so it dissociates completely, so you just do minus 0.11. And then you add it to Ba, but for OH, there's 2 of it, so you have to multiply by 2. So you're going to have 0.11 and then 0.22. So it's asking for the pH, so all you have to do is to do negative log of 0.22 to get the pOH because it's OH. And then you just have to subtract it from 14 to get 13.3424. So question number 9 says the molar concentration of hydronium ion in pure water at 25 degrees Celsius is, so the concentration of water is 1 times 10 to the negative 14. So the Kw is concentration of H3O times OH, which is the same thing as 1 times 10 to the negative 14. So all you have to do in this question, you just have to do the square root to get the concentration of hydronium. Question 10 is a free response question. So it says hydrofluoric acid HF dissociates in water as that equation, and then it gives you the Ka. It says write the equilibrium constant expression for the dissociation of HF. So it's only products over reactants. The only thing is that you don't include water because it's a liquid, and then it's going to be Ka because it's an acid. Part B says calculate the molar concentration of H3O in 0.4 molar HF solution. So you make an ice chart, and then you start with 0.4 molar of HF, 0, 0, and then you have x, x, and then minus x. You do 0.4 minus x, and then you ignore it because it's going to be a tiny number. And then you do products over reactants, and then you have the Ka, so you just set it equal to each other, and then solve for x. X, you get 0.017, which is the concentration of hydronium. So for part C, we have a different equation, which is HF plus OH gives you H2O plus F ion. So it gives you a volume of 15 milliliter of 0.4 molar NaOH is added to 25 milliliter of 0.4 molar HF. Calculate moles of HF remaining in the solution. So what you have to do is to create an ice chart. To find the moles, because the volumes are different, you have to find the moles. So to find the moles, you just multiply the molarity by the milliliters added. This is moles of HF, 0.001, and then you do the same thing for OH, and you get 0.006. So here we plug in those numbers. Since 0.06 is a limiting reagent, you just subtract 0.006 from both sides, and you get 0.004 as the moles remaining for HF. In part C, we have to calculate the molar concentration of F- in the solution. So for part C, you just have the same ice chart again. The only thing is that you have to add 0.006 to the ion over there, and that's going to give you the moles. To find the molarity, you have to do moles over the liters. To find that, you add the volumes that you started with, which is 0.04, and you get the molarity to be 0.15. For part E, we have to find the pH of the solution. So we have the exact same info again. This time we have to find the molarity of these moles. So I divided both of them by the new volume, which was 0.04, to get the molarity. And then you can use the HH method to find the pH. So it's just pH is equal to pKa plus log of the conjugate base over the acid. So it's going to be negative log of the Ka that we're given, plus log of 0.15, which is the conjugate base, over the 0.1, which was the acid, and you get 3.32 as your pH.